Okay, ladies and gentlemen, let's continue with our course in heat transfer. You have previously done chapters 1 to 3 on heat conduction. I have also revised it with a previous lecture, all 3 chapters in one lecture. And today we're going to continue with chapter 4 on transient heat transfer. I'm going to use HT a lot for heat transfer. It just makes, then I don't have to write that much. So HT is heat transfer. And let's see what is being meant with transient heat transfer. If we look at a graph, or 2 graphs of temperature, capital T, as a function of time. Small t is time in this module. Temperature as function of time, and we look at any possible arbitrary body. And it's a 3-dimensional body, and we are interested in a temperature T1, 1, and 1 that would represent X, Y, and Z coordinates, as well as maybe in the temperature at coordinates 2, 2, 2. And this one might be the temperature on the surface, also in an X value, a Y value, and a Z value, which are not the same than those. Now, if we have what we call steady state, and that is what you've done in chapters 1 to 3, then those temperatures would remain constant as a function of time. Okay, so if we would measure the temperatures with a thermocouple or any other body, temperature as a function of time, we would get the same readings. And therefore, it would be known as steady heat transfer. Unsteady or transient heat transfer would be those temperatures may be doing something like that, so it changes as a function of time. Maybe temperature of 2 is doing something like that, and the temperature of 3, something like that. So we can see that the temperature is changing, although it looks as if this temperature is starting to be a constant. There are still changes here in the gradient, and we cannot for sure say that this temperature is going to change to values which are constant and therefore to steady state conditions. So that's a very simple explanation of the difference between steady state heat transfer and unsteady heat transfer or transient heat transfer. So this chapter is about transient heat transfer, so we are interested in how the temperatures in body changes as a function of time. The chapter itself is divided in paragraph 4.1, which is about the lumped system method, and then there's a paragraph 4.2 in which we are going to do PW is plane walls. We are going to do spheres as well as cylinders. Plane walls, cylinders, and cylinders and spheres. Long cylinders and spheres. Then there's going to be a paragraph 4.3 on semi-infinite geometries. Semi-infinite geometries, paragraph 4.4 on multidimensional bodies, and then not in this chapter 4 but actually in chapter 5 there's going to be a CFD approach, so where we solve the heat conduction problems and unsteady problems making use of this discretization method, and or one or other solution to solve it with. And together with that, you're doing the module MKM, in which you're going to do the numerical solution by using the finite element method and the CFD methods. So that is a description of actually if we would like to study unsteady or transient heat transfer problems, where we should look at and what is coming to us. Now, what is very, very important, and students usually have a find it very difficult to understand, is that, of course, the complexity is actually increasing in this direction. The complexity, and in general, also the accuracy. Okay. So we are going to start with the most simple type of approach that you can have, and in general, you're going to see that if we used this system of a lumped system, then the solutions are almost never valid. Almost never. Okay. Or they are going to be not suitable in general. Not suitable. So when is this approach going to be valid? Well, in general, there are two guidelines that we can use, and that is normally to say it is very small geometries, and high thermal conductivity. High K is for thermal conductivity, watts per meter Kelvin, and high values of K. And even those two criteria is not a good enough criteria for us to use the lump system approach with. So let's start with the lump system. The lump system approach. With the lump system approach, we are going to look at any arbitrary body. At the moment, I'm already drawing this body to be big, while I've said normally very small geometries. Okay, but that is just to make things easier so that we can see what we are considering here. And in this body, we've got M, which is the mass of the body. The terminologies that I'm using now, you're going to use all over and over many times. So that's the mass. This symbol for volume, because we cannot use the normal capital V, because that is also being used for velocity. So that is why we make the distinction here for volume, like that. The density rho, and the body is at an initial temperature Ti. Ti is the initial temperature. This body also has a certain surface area, and on the outside it has a heat transfer coefficient H and a certain T infinite, and that is the temperature of the environment. So what we know about this body at this stage is if we look at the curve of the temperature as a function of time, is that the initial temperature of this body is Ti. And the assumption is made that that has been the temperature for quite a while. So the body is in a steady state situation before at T equals 0 it is going to change. So before that, it is in a steady state condition, and now it is going to change because this temperature is different than that temperature. And in general, you're going to see that this temperature change is going to do something like this. and it will be described by equation 4.4. So this temperature is going to reduce. This temperature here is going to get less, and that will only happen if the initial temperature is higher than that of the environment. So typically that would be the trend. Well, the trend would be something like that, and it will still be described by equation 4.4, but that would be if the temperature of the environment is larger than the initial temperature. Now let's get to equation 4.4, and we do that by looking at the heat transfer, HT, is the heat transfer into the body, the heat transfer into the body during the time period dt. So we are considering the heat going into the body. Doesn't matter if this temperature is now higher than that one. We always look at the heat going in or out. One of the two, it doesn't matter. And in heat transfer, it is easy. We normally take the highest temperature minus the lowest temperature. But at this stage, it can be any way around. So the heat transfer into the body during dt should be equal to the increase in the energy during dt. So the heat transfer into the body should be the increase in energy into the body. If this is a volume with water in it, 200 liters, and I would like to add some water to it at 10 liters per second, then the heat transfer, the 10 liters per second, is equal to the increase in the mass of the volume, isn't it? So it's a very simple concept. The heat transfer going into the body, you've already done convection heat transfer. That would be equal to the heat transfer coefficient multiplied by the surface temperature, and the temperature T environment minus that temperature. So we assume that the heat transfer is in that direction. So the heat transfer into the body is equal to the increase in mass, the increase in energy, and that you've also done in thermodynamics as well as in physics, and that would be equal to the M, the Cp value at the constant pressure. The pressure doesn't change, dt, the change in temperature. Now, if we look at the mass can be written as rho multiplied by the volume, the density multiplied by the volume, and dt we can write as dt minus T infinite, because that value is considered to be a constant. So that value is not going to change. It is only going to be the temperature of the body that's going to change. If we do a differentiation here, dt, if this is a constant, it is equal to 0. So that is why we can write dt as equal to d, T minus T infinite, T temperature infinite, yeah. So let's just rearrange it, and then we can rewrite it as the heat transfer coefficient multiplied by the surface area, T infinite minus T, dt is equal to rho V Cp dt T minus T infinite. Or in terms of getting all the temperatures to the left side, like that. We would like to do the integration. T minus T infinite of T minus T infinite. That's the same as 1 divided by x. We are going to assume that the heat transfer coefficient and the area is a constant, as well as the density, the volume, and the Cp value, and dt, like that. So we assume that all of this stays constant. It's not a bad assumption. And when time is equal to 0, then that temperature is Ti. And when the time is equal to T, then that temperature is equal to capital T. You know how to do the differentiation and to clean it up. If you do that, then you're going to have the ln of the temperatures difference divided Ti minus T infinite is equal to minus the heat transfer coefficient, the surface area, rho VCP. I'd like to get rid of the ln term. So the temperature distribution divided by Ti minus T infinite equal to e to the minus bt. Okay, b is just a constant, which is equal to the heat transfer coefficient, the surface area, divided by the density, the volume, and the Cp, with units 1 divided by second. And this is the equation 4.4 that we've been referring to. Okay, so this is the lumped system solution, showing what will the temperature in the body do as a function of time. Take note, I say that this approach can almost never be used. Okay, so it is the simplest possible approach. Normally it can only be used for very small geometries and high thermal conductivities. Now, with the solution of this method, people have also took the results and they compared it to that of experiments. And they have found that in most cases this solution is not valid. However, there are cases where it is quite valid and where it is accurate, and where solutions can be obtained from with errors of maybe 5 to 15%, depending on the following criteria. And that is by using the characteristic length, which is the volume divided by the surface area, and defining a so-called Biot number. Biot number, like that, Biot, the Biot number, which is equal to the heat transfer coefficient multiplied by the characteristic length divided by K. And normally, if the Biot number is smaller or equal to 0.1, then this approach can be used. Now at this stage, I already want to say or point it out. This approach is not valid for paragraphs 4.2, 4.3, for the rest of the textbook. In the rest of the textbook, the Biot number is not going to be defined like this. In the rest of the textbook, for example, the Biot number for a plane wall is going to be 2L. PW, plane wall. For a long cylinder, it is going to be the radius. Cylinder. And for a sphere, also it's going to be the radius of the sphere. So please, you use it for this approach only and never afterwards again. Okay, so please be careful that you do not do that. Now what does this thing actually mean of the Biot number? The Biot number, what it actually does, it is the ratio of two resistance terms. In the first 3 chapters of this textbook, and in my previous lecture on which I've given you an overview of conduction, I have reminded you that in heat transfer, the resistance for heat transfer can be written in the same format as you've done for your courses EIR, okay, where we consider this as the resistance R of conduction, COND, the resistance of conduction. And here is the resistance of convection. Now take note, I'm making this one much larger than that one. So this is the resistance of convection. And that is T environment, and that is T initial. So the Biot number is actually a ratio of the internal resistance of conduction to the external resistance of convection. So it's very easy to see, this is the internal resistance of conduction, so that term is that value there, and the convection is that value. It therefore means that for the heat to get there, this resistance has a negligible effect. Most of the resistance is in this term. And because of that, the temperatures in that whole body is the same. Take note of the solution. This solution only gives the temperature as a function of time, but it doesn't define the temperature at a specific point. It therefore means that all the points inside the body is at the same temperature. It tells us how the temperature changes, but inside there are almost no temperature changes. Does that sometimes happen? Yes, again with small geometries and high thermal conductivity bodies. Then that typically happens. You must think of yourself of all of you waiting outside, and at t equals 0, all of you are so anxious to get into this heat transfer class. All of you are trying to get into class as quickly as possible. Now, this resistance is being determined by the doors. At the moment you're through the doors, there are lots of space for you to move around. And that is typically what this ratio means. It means that the conduction resistance is negligible in comparison with this resistance. So typically it's 10 times and more. So if this is 10 ohms in resistance, then that resistance should be 1 ohm or less. That is what that ratio actually means. And for those types of problems, then this approach would work very, very well. Now, if you think of possible bodies for which this will work very well, a small Biot number, you can get a small Biot number if the heat transfer coefficient is very small. When will the heat transfer coefficient be small? It will be small in an environment in which there's actually only natural convection. So like here in this venue, there's no fan or anything that actually forces the air over you. Yes, there's a fan forcing the air into the venue, but let's put off the fan. If you put off that fan and there's no air coming in at a low temperature, you're going to have an environment of natural convection. However, if I would use a fan, a big fan, then the heat transfer coefficient will increase, and the heat transfer coefficient will even increase more if I do not use air, but for example, water. So if I use a water jet and I would spray it on you guys, the heat transfer coefficient will become larger. So small Biot numbers are being caused by environments where the heat transfer coefficient is small. So normally natural convection. Then secondly, if the geometry is very small. Now, what geometries can you think of which are small? Well, small geometries would typically be a ball bearing, a small ball bearing. Small ball bearing will be small in diameter, so any object that is very small. And then the thing that really also helps is the thermal conductivity. If the thermal conductivity can be as high as possible. So which bodies has a high thermal conductivity? High thermal conductivity would be bodies like diamond, a diamond ring, for example. Okay. The thermal conductivity of diamond is the highest, and normally, as you know, diamonds are very small in geometry, so any diamond inside a ring will be an excellent example of where the Biot number will be very small. And therefore, the temperatures as a function of time will be described very well by that equation. Other geometry is the ball bearing that I've used. For example, normally ball bearings are being made from stainless steel, and stainless steel, copper, aluminium, they all have a very high thermal conductivity. So again, that will cause the Biot number to be very, very small. So those are examples of geometries and bodies whose temperature behavior can be described very, very well by this approach. Now let's do an example, and that would be example 4.13. So there are examples in the textbook worked out, but I'm specifically not using those examples so that I can give you supplementary examples that you can work through. So the example I've chosen is example 4.13, and I also didn't do it last year in class. So every year I'm trying to select some new ones so that if you go to the videos, you also have a large variety of examples to choose from. Now this example, I actually didn't think is going to be described very well by the lump system method, but at the end it was, or apparently it seems, and that is of a brick. A brick with dimensions of 203 millimeters, 102, and 57 millimeters. The initial temperature of the brick is 1,100 degrees Celsius, so it must be in a kiln or something like that. Then the environment temperature is being dropped to 30 degrees Celsius. The heat transfer coefficient is low, natural convection environment, 5 watts per square meter degrees Celsius or Kelvin. The density of this brick is equal to 1,920 kilograms per cubic meter. The Cp value is equal to 790 joules per kilogram Kelvin, and the thermal conductivity is 0.9 watts per meter Kelvin. Okay, so for me there were two reasons when I originally thought this cannot be, and that is that the K value is low, relatively low. It is not that of a metal, like copper or aluminium, who has K values of 200 or 300 millimeters. Yes, and the dimensions are not that small. Okay, now remember this approach of calculating a characteristic length and then the Biot number is only valid if you try the lump system method. It is not valid in the rest of the chapters and in the rest of the textbook. So I cannot warn you enough on this. So if we calculate the characteristic length, it says it is the volume divided by the surface area. The volume of the brick is 203 millimeters, so it is 0.203 meters multiplied by 102, so it's 0.102 millimeters, and 57 millimeters. That is the volume of the brick, divided by the surface area is 2 times 0.203 multiplied by 0.12. So it is this area on this side as well as on the other side, 2 of them, plus 2 times 0.102 multiplied by 0.057. So it is this area here and also on the opposite side, plus 2 times 0.203 multiplied by 0.057, 57 millimeters. And the characteristic length to me looks very small because it's only about 15 millimeters. Maybe I made a mistake in the calculations. You can go and check it at home. Okay. Now we can calculate the Biot number. The Biot number is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. The heat transfer coefficient is 5. The characteristic length is 0.01549 divided by the thermal conductivity is 0.9. So that is equal to 0.0861, and that is smaller or equal to 0.1. So apparently the Biot number approach can be used for this example. I'm very skeptical, but in any case. Okay, B, the B value is just all the constants that we have to use. the heat transfer coefficient multiplied by the surface area rho v Cp. So B is equal to the heat transfer coefficient, the surface area, rho Cp, and the volume. Okay, you can go and calculate it at home. All the values are there. The heat transfer coefficient multiplied by the surface area. Here's the surface area, divided by the density, which has been given. That is 1920. The Cp value and the volume again, like this. But however, you can also, if you look at this, actually see that this is the characteristic length. So it can be written as the heat transfer coefficient divided by rho Cp, the characteristic length. And if you go and calculate the B value, it is 2.128 multiplied by 10 to the minus 4 per second. Oh, I forgot to mention. So the original problem was that is the initial temperature. The environment temperature is being dropped to 30 degrees Celsius. And we are asked to calculate how much time it will take for the temperature to be 5 degrees Celsius from the ambient temperature. So the ambient temperature has been dropped to 30. So the question is, how long will it take for the brick to get to a temperature of 35? Okay, so the lump system approach says the temperature as function of time, T minus T infinite, divided by Ti minus T infinite is equal to e to the minus bt. We would like to know when is the environment temperature at 35. Not the environment temperature, the temperature of the brick. When would the temperature be at 35? It was originally at 1100, and the environment temperature is 30. So there's a 5 degree Celsius difference. It's equal to E to the minus B is equal to 2.128 multiplied by 10 to the minus 4 multiplied by T, the time in seconds. So the solution is that T is equal to 2.522 multiplied by 10 to the 4 seconds. So about 25,000 seconds. If we divide that by 60, we can get it in minutes, and then again by another 60, and then we can calculate. It will be about 7 hours. So 7 hours for the temperature to drop. From 1100 to 35 degrees Celsius. Take note that this solution, if we are looking at the temperature exactly in the center of the brick. Now with this sketch, it looks as if it's on the surface, but it's exactly in the center. So if we are looking at that temperature and this temperature on the surface, okay, and of course maybe that temperature there, also on the surface. then this solution would give this type of trend, the temperature as a function of time. The temperature to decrease to 35 degrees Celsius. So that would be 7 hours. Okay. But the thing that you need to understand is, if you look at the temperature in the center, then that is the solution of it on that line. If you want the temperature on that surface, on the outside, it's going to give you exactly the same solution. Okay? And again with the other temperature. So the lumped system approach cannot differentiate between different positions inside a body or on the outside. All the temperatures would remain the same. And normally that type of approach would give excellent results for bodies which are very, very small. That is small. So K is very high, that is very small, and the heat transfer coefficient very small. So those types of bodies, like a ball bearing, a diamond that you put in your diamond ring, typical geometries like that. There, if you would go and measure the temperatures in the center and the surfaces, you will almost not measure any temperature difference. Any questions, ladies and gentlemen? If not, then thank you very much, and then I'll see you again tomorrow.